So in this section, we're looking at complex numbers, or better, complex numbers that contain I, that are considered imaginary numbers. If you recall, when we had the square root of 9 or radical 9, we agreed that square root of 9, because it's 3 times 3, square root of 9 is 3. And when we came across the square root of negative 9, since there are no two values that are exactly the same that will give me negative 9, we said this is not a real number. Not a real number. Right? We have real numbers which could be broken up, right? We have rational and irrational. But above real numbers, all real numbers are part of the complex number system. All real numbers are complex numbers. And all imaginary numbers are complex numbers. So real numbers are complex numbers and imaginary numbers are complex numbers. So when I have the square root of negative 9, I could break this up as the square root of 9 times the square root of negative 1. The square root of negative 1, we're going to set equal to I for imaginary. So now we're going to have the square root of 9 is 3, and the square root of negative 1 is I. So the square root of negative 9 is equal to 3I. Well, if you're going to accept that I is equal to the square root of negative 1, then I want you also to accept that I squared is equal to negative 1. And if we accept those two, we'd be able to find I to the third, I to the fourth, I to the fifth. Let's think about these, just for fun. I to the third, right, would be I times I times I. That would be I to the third. Or we could say it would be I squared times I. And I squared is negative 1 times I. That would make this negative I. I to the fourth would be I times I times I times I. Well, I know I squared is negative 1. So I have negative 1 times negative 1, which would be positive 1. So I to the fourth would be positive 1. Then I to the fifth would be I times I times I times I times I. So this would be positive 1, I to the fourth times I. 1 times I is I. I to the sixth would be I to the fourth times I times I. So it would be I to the fourth, we said was 1. I times I is I squared, which is negative 1. 1 times negative 1. I to the seventh would be I times I times I times I times I times I times I. It would be I to the fourth times I to the third, which is negative I. And then I to the eighth would be I to the fourth and I to the fourth, which would really be 1 times 1, which is 1. So my point of doing this is to show how this pattern repeats, right? It goes I, negative 1, negative I, 1. I, negative 1, negative I, 1. I, negative 1, negative I, and 1. In fact, we could see that every I that's raised to an exponent that's divisible by 4, 4, 8, 12, will always be 1. So if I look at something like this, I to the 43, I could say, well, that's I to the 40. I know 4 goes into that, so that's equal to 1. I to the 40 times I to the third. And I know I to the third is negative I, so it's really 1 times negative I. We could do it that way, or another way would be just to divide 4 into this exponent. You could say 4 goes into 43, right? 4 goes into 4, 1. 1 times 4 is 4, is 0. And then you bring down the 3, and 4 doesn't go into 3. Or 4 goes into 3 0 times. And 0 times 4 is 0. So you have a remainder of 3. So that remainder will always be your exponent of I. So here we had a remainder of 3, so it's going to be I, or rather negative I. Here, if I divide 4 in, it goes evenly. 4 goes into 32 evenly. So it's like the 12 or the 8. So it's just going to be 1. Right? So that would just be 1. Any multiple of 4 would be 1. Oh, I have another. 100 is a multiple of 4. Why did I do that? That's not a good example. 100 is also a multiple of 4. 113 is not, but 112 is. This could be written as I to the 112 and I to the first. I to the 112 is 1, and I to the first is just I. So I to the 113th power would just be I. So you could always break it up as a multiple of 4, like 40. Right here, we broke this up as 112 and 1. And whatever the remaining value is will always be broken up as either I to the first, I to the second, or I to the third. So it'll either be I, negative 1, or negative I. If it's a multiple of 4, it's always 1. Just something to think about. These 4 operations are relatively easy, so you don't have to worry too much about it. What we want to be aware of is standard form of a complex number is always A plus BI. Always let your imaginary term be the last term. Imaginary term always comes last. So let's do some examples. So here's an example of a subtraction and an addition problem. Right? And actually, these problems work just like regular polynomials. When we add and subtract complex numbers, really, we want to remove the parentheses and combine like terms. So in this subtraction problem, To remove the parentheses, we're going to distribute. So I'm going to have 4 plus 3i minus 7 plus 1i. I remove the parentheses, then I can combine my like terms, always putting my real number first and my imaginary last. So 4 and negative 7 is negative 3. 3i plus 1i is 4i. That's it. Addition, the same thing. We distribute. We're distributing this 1, which doesn't change anything. We have a 1 out here. Doesn't change anything. So I'm going to have negative 2 plus 6i plus 4 minus I. I combine my like terms. This looks like I'm going to have 2 plus 5i. Here's a multiplication problem. And just like with regular polynomials, we're going to take what's on the outside and distribute it to what's on the inside in order to remove the parentheses. So here I have a negative 8i times 2i. Negative 8 times 2 is a negative 16. I times I is I squared. Negative times negative is positive. 7 times 8 is 56. 56i, right? 7 times negative 8i will give me 56i. This could be simplified because we know I squared is really negative 1. So this is negative 16 times negative 1, which is positive 16 plus 56i. Right? We always want to make sure our imaginary comes last. So here's 2 more multiplication problems. It's a multiplication of binomials. So we could FOIL these. And we distribute our first term. That gives me negative 12 minus 4i. And then 8 times 3 gives me a negative 24i minus 8i squared. I combine my like terms. It looks like I'm going to have negative 12 minus 28i minus 8 times negative 1. Well, I know 8 times negative 1 is positive 8. So I can combine that with my 12. They're like terms. And it looks like my final answer is going to be negative 4 minus 28i. Right? Because my negative 12 and my positive 8 give me my negative 4. This is a positive 8 because it's a negative 8 times I squared. We said I squared was negative 1. Always. Here, this is a binomial squared, so we could use the binomial squared formula, or we could expand it as 5 minus 2i and 5 minus 2i. And it would be the same procedure. We're going to distribute. So we're going to have 5 times 5 is 25 minus 10i minus 10i plus 4i squared. So it's 25 minus 20i minus 4, because that's a negative 1. I combine my like terms. 25 and negative 4 is 21 minus 20i. If we're going to divide, we could look at this as division. It's 3 divided by 4 plus I. But really, we want to make that denominator a rational value. Right now, it's a complex number that contains I, or an imaginary value. So we're going to do the same thing that we've done to rationalize any denominator that's a binomial. We want to multiply by the conjugate, which in this case would be 4 minus I, and we want to do that to the numerator and the denominator. Let's keep going out of focus. So we multiply the numerator and denominator by 4 minus I. So up top, this is going to give me 12 minus 3i. On the bottom, since it's conjugates, you could just multiply your first with your first and your last with your last. So that'll be negative I squared. So it looks like I'm going to have, over here, 12 minus 3i over 16 minus a negative 1. Well, 16 minus a negative 1, well, that's really plus. So it looks like I'm going to have 12 minus 3i all over 17. Which is nice, except for it's not in standard form, right? Standard form has to be a plus bi. So you want to break this up. You want to divide both of these terms by 17. So this is really going to be 12 over 17 minus 3i over 17. You always want it in that a plus bi form. That's the way it'll be in the back of the textbook. This next example is a little more challenging, maybe. You might want to take a second and try this one, and then I'll follow you. I'll work over it in a minute. So in this example, we'll continue on. We're going to multiply by the conjugate, which would be 4 minus 3i. 4 minus 3i to the numerator and the denominator. Well, the denominator is going to be pretty easy, so I'm going to do that first. 4 times 4 is 16. 3 times 3 is negative 9i squared. We're going to have on the bottom, right? We just have to multiply these when we have conjugates. On the top, we're going to have to distribute. 3 times 4 is 12. 3 times 3 looks like negative 9i. 4 times 4 is negative 16i. And 4 times 3 is positive 12i squared. Let's simplify this a little bit. I have some like terms to combine. So I'm going to have 12 minus 25i minus 12, right? Because this is a negative 1. So 12 times negative 1 is negative 12. All over 16 minus, or I guess we could say plus plus 9, right? Because this is -1 also. So I have 12 minus 12. These are gone. -25i is up top. And 16 plus 9 is 25. So -25 divided by +25 is just -1. So my final answer is just -I. So it's all relatively easy, but in fact it gets easier because all of these problems that we just did could be done on your calculator. It could be done on your TI-83 or TI-84 graphing calculator, and I'll show you how in a second. Okay, so let's look at that last example, which was one of the hardest examples. It said 3 minus 4i, and I could find my I is right here. You see it right down there above my decimal point. So I'm going to do second decimal point, close parentheses, divided by open
Would it be
parentheses.
Sorry, would it be possible to make the calculator a little bit wider? Yeah, that's perfect. Thank you. Oh,
You could see it now?
what you just had before.
Because I'm not seeing a calculator at all anymore. Hold on a second. Can you see it now?
I do, it's just really narrow.
I don't think I could change the size of it.
Okay.
What's that? Oh, keep losing it. Okay, let's see what we could do here. So it's divided by 4 plus 3i, close parentheses, enter, and we get -I. Right? And even the one before that, we had 3 divided by 4 plus I, enter, gave us that horrible thing. But now if I do math, change it to a fraction, enter, enter, it gives me 12/17 minus 3/17 I. The only thing I don't like about this is the I looks like it's in the denominator, but it is not. It's 3/17 I. So really that I belongs either in the middle or in the numerator. But all of these could be just done on your calculator, right? You could just do 5 plus, whatever, 2i, minus, -18 plus I. Right, and your calculator will do it for you, and always leave it in standard form. So all of these problems we did by hand. You don't have to. They could all be done on your graphing calculator pretty easily.
How'd you do the fraction again? How'd you put it in fraction form through the calculator?
Division sign would be your fraction bar, right here. 3 divided by, and then in parentheses, whatever's in the denominator.
Oh, I meant like when you put like answer and then fraction.
Oh yeah. Anytime you have any kind of bad decimal, like you can say 0.25, right? If I want to change that to a fraction, you hit math, and you see it says frac, and then you just hit enter, enter. It's math, enter, enter will change decimals to fractions.
Oh, okay. Thank you very much.
You're welcome.